morning. I'm glad to take this opportunity to share with you our effort and progress in this new Phosphorus initiative. Actually, the center started this project back in 2022. So before I get to the technical part, I prepared a slide to overview on phosphorus cycling. I think Lee did a wonderful job explaining all the problems and so on. I'm not going to spend too much time in this slide, but there are two things I want to emphasize here. So unlike nitrogen that we have the gas form that we can get rid of them from the wastewater, phosphorus has to be transformed either between the liquid form or to the solid form. So we have to deal with it when it finally get to the ecosystem, especially in the aquatic system in fresh water. So when the excess phosphorus get to the freshwater system, it causes a problem of the algal bloom. And also, no matter what forms of phosphorus we're dealing with, from organic phosphorus to polyphosphate, finally it will be degraded to the simplest form of orthophosphate, phosphate here. So when we look into these phosphorus contamination sources, we typically divide them into two major categories. The point source contamination, such as the municipal wastewater treatment plant, and also the on-site or non-point source contamination, such as on-site systems or agricultural application and so on. So unlike the municipal wastewater treatment plant, you can expect typical phosphorus levels in their influent, but in the on-site wastewater, we have a wide range of phosphorus concentration you may expect. And also, unlike the municipal wastewater treatment system, you may expect the federal level or state level regulations in terms of the final effluent phosphorus concentration charges. However, for on-site wastewater, you can see in this map, we look into some of the database to see that among the states for now, in 2024, only a few states have the regulations to regulate the final discharge of the effluent from on-site systems. You can see the range is also pretty wide, from 0.3 to 4 milligram per liter. So why is that? So let's take one step back to look at the very complicated phosphorus transformations in the subsurface or in the soil. So in this figure, you can see in the septic tank effluent, so basically the phosphorus can be in all different forms, together with a lot of cations present. So when the septic tank effluent get to the leaching field, which is a typical type of on-site wastewater systems, we typically consider within 1 meter from this leaching field is a phosphorus rapid transformation zone. A lot of complicated physicochemical reactions can take place. And after these water further get into the, I forgot to mention the plant uptake. So it definitely contributes to some level of phosphorus removal, but not that much. But when the effluent really get to the saturated zone or meet the groundwater flow, you can see here is a very complicated process, like adsorption, desorption. These are reverse processes, and also the precipitation dissolution can happen simultaneously. A lot of environmental factors, such as the pH change or the redox condition change in the subsurface or the soil profile composition change, as well as groundwater flow change, will all impact this complicated phosphorus transformation process. So when we look into the literature with dozens of literatures looking into this problem, we found contradictory results in terms of whether our current leach field-based on-site system is effective to attenuate or remove phosphorus. So that leads to us to think about what are we going to do to deal with this phosphorus pollution, especially in the upstate New York, we have hundreds of freshwater bodies that may face this problem. So basically, we first ask ourselves, what are the major knowledge gaps and our research opportunities? And based on the findings, then we further look into three separate coherent research areas that I'm going to explain in my following slides. So the first question, so let's first look into the literature to see what are the current available technologies that can be applied for phosphorus removal and recovery. So as you can see in this slide, we categorize them based on the different removal mechanisms. So basically they include the physical-chemical approaches and biological processes, soil-based processes, as well as source separation. As Dr. Wah explained that the center has been working on source separation for both nitrogen and the phosphorus removal. I'm not going to emphasize that in my talk today. So basically, we first rule out a few processes that are not quite feasible for on-site applications. And then with the three removal mechanisms, we further look into what are the opportunities for us to conduct our research on. So as you can see in this slide, we summarize the 4 promising systems or 4 technologies that we actually are currently working on. So they are passive filters, soil-based treatment systems, the electrochemical approaches, as well as source separation. So here we listed a few promising systems and also the opportunities that we can explore. But more importantly, I want to emphasize before I get to the technical details is that when we try to identify the solution for each specific condition, it has to be site-specific. For example, we can see whether those houses or residential places are distant or they are grouped like a community or cluster of houses. That would determine like what best technology we can choose. So basically, we're looking into all these 4 approaches, and then I'm going to move to the 3 research areas we're currently working on. So the first part is to understand the phosphorus fade and transport in current on-site system. We want to have a database or baseline to understand what is really going on. Before I talk about the experimental details, I want to present these slides to summarize our research and development team in these 3 major areas. As you can see, we have from research consultant to postdoc, graduate students, and also research scientists, and as our technical support specialists. And also we have collaborators across the campus from different departments. So basically, I'm going to present on behalf of our entire team today. All right, so the first research area, to understand phosphorus fade and transport, I'm going to give you 2 examples of our effort locally in Long Island, Suffolk County, so about our long-term monitoring of the NRB system. I also would like to explain like what we are doing in the upstate New York. So as you have learned from Dr. Wa's talk, so we have been monitoring the 3 different configurations of NRB for the past few years. So in addition to the nitrogen analysis, we also collected samples for some phosphorus analysis. As you can see here in this figure, the y-axis, the total phosphorus concentration in our influent and effluent. And these are the data collected from the last year based on a quarterly measurement. So in summary, so when we look into the performance of NRB systems, we summarize the data, and you can see here, basically for the 3 types of NRB, lined, unlined, and the box systems, they all achieved very good removal performance from 60% to even 90%. So is that really the case? So basically, because this quality measurement is kind of a snapshot of the system performance. So we want to understand whether the systems are really effective to remove phosphorus. So basically what we did is we constructed lab scale column, try to understand within the sand filter or nitrification layer, whether they can do this phosphorus removal. So this work is led by our postdoc, Dr. Wang. We also have a poster in the hallway for all the details. So basically, we constructed sand columns using an aged sand from a 5-year-old NRB system. We also constructed columns using the clean sand. So we have been applying the real septic tank effluent to see whether those sand columns can retain or remove phosphorus. So in general, so this figure shows you the overall removal efficiency. You can see that actually for both types of sand, they can only remove 20 to 40% in overall phosphorus, which indicates that the sand itself cannot achieve a long-term phosphorus removal. So considering the like a storm event or heavy rain, those phosphorus being attenuated can be leached out. So that is about the study at Suffolk County, but also in upstate. So we have been working with Cayuga County, Tompkins County, and a few other communities to identify a study sites that we can do a monitoring to look at their on-site systems performance. So here is an example, like you can see here is a Lake Como, which is located in the sub-watershed of Cayuga Lake. So with one identified site, so we actually installed several monitoring wells, and also we collected soil samples for soil profile analysis. So these projects include 4 major stages or phases. So here we have finished the first 2 phases. Basically last year, 2023, we have identified a bunch of lists of the potential study sites, and we did our initial sampling trip. And after we address some of the challenges, so this year, actually, last week, our team just finished our second round of field trip, which was quite successful. We installed several piezometer wells, and we collected soil samples back for lab analysis. As you can see here, we can do like nutrient analysis as well as soil profile analysis. So our plan, like after we install these piezometer wells, after 1 year of monitoring, we'll be able to install the identified phosphorus removal technology that we are working in parallel. So we can install those technologies and for long-term monitoring. So now let me switch to the second research area, which is to screen, validate, and recommend commercial products. So we first conducted a review to see what are the technologies available on the market, and then what are the promising technologies we are going to further investigate. So here I'm going to talk about our findings and also our experimental results with 2 identified technologies. So in this table, it's pretty busy. Basically, we just ranked the top 12 commercial products that on the market. You can see actually they are from all over the world, from Europe, North America, Japan, and so on. So we group them into 3 major categories. They are filter-based media, or they can be electrochemical approach, and also the last one is the metal salt dosing, which is actually the current practice in large-scale wastewater treatment plant. So after we do the assessment of these technologies, we actually we worked further on the top 2 technologies and conduct bench scale to pilot scale studies. I'm going to give you an example in each of the project. So this bench scale screening and pilot testing is led by our PhD student, Mr. Fan Jianzeng. We also have a poster out there. So here is a table giving you 3 examples of the media materials we identified. So they are called polonite, filtrolite. So these 2 materials are from North Europe. And actually, they have been demonstrated to be successful removing phosphorus from on-site systems. There are over 1,000 installations overseas. We also identified a local materials, which is called wollastonite. It is available in New York. So we actually, with these 3 materials, we conducted a series of bench scale adsorption kinetics and isotherm studies, and we're trying to compare their performance in terms of their capacity to remove phosphorus. So here you can see in this figure showing you that polonite and wollastonite, actually in the batch scale condition, they can remove over 60% of phosphorus from the solution. So then we continued working on these 2 materials. As you can see, we purchased 3 cubic meters of polonite overseas from Poland. And also we bought quite some buckets of wollastonite in different shapes, like formations, for further studies. So basically for polonite, I want to give you an example what we're doing. So in pilot scale testing, we are trying to establish this SOP in order to compare different types of the media. So we found in the literature, a lot of discrepancy is due to the not uniform study system. So here instead, so we constructed the columns in the research trailer that we can feed them with real wastewater. So with this setup, so we can test several operation parameters, very important ones, such as the hydraulic residence time. It will tell you how big your system is when you're treating a designed loading, and also the influent composition that would determine where we are going to put this phosphorus removal module to your entire treatment train, and also the flow pattern, whether you apply gravity-driven or you use upflow condition. So here are a few photos we took from our real system setup. So I'm going to share with you a result in terms of the hydraulic residence time impact on the medium performance. So here is the figure showing you that when we use polonite as the filter media, so we tested them with a real effluent from our NRB systems. And you can see in this figure, the black squares are our influent phosphorus concentration. And when we apply a low HRT 2.5 hours, those red squares indicate the breakthrough happens after 1 month of operation. But if you increase HRT to about 10 hours, the breakthrough would happen in about 6 months, which indicate HRT is a critical factor that will govern the overall system performance. So in addition to the media filtration, I also want to mention another important research area we have been working on is electrochemical technology. So here in this slide on the left, you can see this is a schematic drawing to show you the removal mechanism. So basically, electrochemical technology is a very mature technology in the water industry to deal with a variety of different contaminants. So specifically in our case, so you can see when you apply the electric current, so in the anode, in this case, this red anode is made of iron plate. So the ferrous iron, just iron 2+, will be released from the anode. And when oxygen is present in the water and also with the phosphate, they will precipitate down phosphorus from the wastewater. So there are already commercial products available. People are using different electrodes such as aluminum, iron, or other metals, basically following the same mechanisms for precipitation. They can install it to the current on-site system in the septic tank. So in our research effort, we are trying to validate the system performance, the phosphorus removal efficiency at different working environment with different wastewater sources. And also we try to figure out the longevity of these electrodes and the maintenance frequency. So this work is led by our postdoc, Arif Riza. We have a poster with more details, but here I want to give you an overview. We set up a lab scale or bench scale electrochemical module that we have been testing. So this is an example showing you the two different combination of electrodes. The green bar is the aluminum and the stainless steel combination. The red one is iron and stainless steel. So basically you can see after about 45 minutes operation, so the aluminum one can achieve over 80% of phosphorus removal. So currently we are working on the system optimization by looking into several operation parameters, including the current density, pH, the concentration of phosphorus, as well as the mixing speed and different combination of electrodes. So the last part I want to go over is our effort on developing new technologies for phosphorus removal and recovery. So in these aspects, I'll be giving you two examples. The first one is to develop the bio-based phosphorus removal materials, and then I will briefly talk about the sensor work we are working on. So this work is led by our PhD student, Xinwei Jian. We also have a poster out there for the details. But here, we use the oyster shell as an example to show you how we make these materials available. So oyster shell is quite abundant, like locally on Long Island, and it has been used for multiple purposes, like for reef restoration and so on. However, when we look at these materials, we really look into the composition. So as you can see here in this workflow, so for the raw oyster shell, it is majorly made up of inert calcium carbonate. So by applying some thermal modifications, we are able to convert these calcium carbonate to the active calcium oxide, which can be used as an adsorbent for phosphorus removal to precipitate down phosphorus. So what we did is we applied two different approaches to modify the oyster shell. So I'm going to show you the result very quickly. So in this figure, you can see with the first bar here, with the raw oyster shell, it can remove about 20% of phosphorus from the solution. But if we apply pyrolysis, which it means like you increase the temperature to about 500 degrees Celsius without oxygen, where calcination is much simpler, you can have oxygen during this thermal modification. Actually, with 800 to 900 degrees Celsius, actually the modified biochar can remove almost 95 to 98% of the phosphorus, which makes it a very promising product for us to use to integrate to our on-site treatment systems. All right, so with that success, we think about, okay, probably we can also use other bio-based materials such as eggshells or clamshells, which are rich in calcium, or biochars, as Xinwei mentioned, and also like even the farm waste. By applying a proper chemical modification, we'll be able to convert them to a phosphorus absorption materials. I want to give you a very brief example. This is a collaboration with Dr. Xiao in chemistry. So we are using the agricultural residue, which is abundant in cellulose. By applying a modification technology called NOP, we are able to modify the cellulose with different functional groups. So basically, we can remove not only phosphate, as I indicated here, we can also remove other nutrients such as ammonium and nitrate. All right, so last but not least is the phosphorus sensor development, as this work is led by Dr. Zhu. We have a poster with more details here. Here is just a schematic drawing to show you what the system looks like. So basically, we're converting all the forms of phosphorus to the phosphate and using the colorimetric approach to detect its concentration. So here is a prototype of this phosphorus sensor. And this sensor can be used to measure phosphorus concentration at ppm level to around 2 ppm. We're also looking into an alternative phosphorus sensor using fluorescence, which can capture even lower concentration at ppb levels of phosphorus. With all those discussion, I also want to mention what are our next steps, the future work. So we will continue our effort to monitor the phosphorus removal performance from all different types of on-site system for long-term monitoring. And based on the pilot scale studies, we will be able to recommend the commercial products to the upstate communities. And in terms of development, we aim to develop a modular-based filtration system that can remove nitrogen and phosphorus simultaneously. Finally, we want to further explore the options of the phosphorus recovery technologies and how do we integrate them into our current effort such as filter reuse or source separation. And also, we will provide the guidance documents to the communities and also provide advice to the upstate communities. I think that will conclude my presentation, and I'm glad to take any questions.